Good morning, all of you. In the last period, we have studied the application of the Gauss law, that is Gaussian pillbox. And now, in the last article from this chapter, we have to study a very important article, that is a Poisson's equation and the Laplace's equation. We are going to discuss on this lecture. First of all, we have to study about the Poisson's equation. What are the Poisson's equation? Differential form of the Poisson's equation. First of all, we have to study the Poisson's equation. After that, we have to study the Poisson's equation in Cartesian coordinate system, spherical coordinate system, and then later on we have to write the form of a cylindrical coordinate system. These are the different forms of the Poisson's equation we have to discuss in this lecture. First of all, we have differential form of Gauss law. What is the differential form of Gauss law? Differential form of Gauss law in electrostatics. What is the differential form of Gauss law? That is, we have to say that divergence of E bar is equals to rho upon epsilon 0 is equals to rho upon epsilon 0. This is the differential form of the Gauss law. In electrostatics, we have to already known. This is equation number 1, where E bar is the electric field intensity, but E bar is equals to, what we have to say that is minus of gradient of V. E bar is equals to what? Minus of gradient of V. We have to further more purely electrostatic field, we have to consider E bar may be expressed as a minus of gradient of potential V. Minus of gradient of potential V. This is the consider as what? A gradient, and gradient of potential of what we have to say that V, and that is we have to put in equation number 1. Substitute this value in equation number 1. What you have to get that divergence of minus of gradient of V is equals to rho upon what we have to say that say epsilon naught. But we have to take the negative sign is outside, and it gets that minus of divergence of gradient of V, minus of divergence of gradient of V is equals to rho upon epsilon 0. Now here divergence of gradient V is a property, and that is what we have to equals to what? We have to say that is equals to del square into V, and here negative sign is minus rho upon epsilon naught, and this is a Poisson's equation. This is the Poisson's equation. It is also called as what? Del square is a Laplacian operator. Del square is called as what? Laplacian operator. And here V is the scalar potential, say V, and after that rho is the surface charge density, epsilon 0 is the permittivity of free space. In the evidence that Laplacian is a scalar, del square is a scalar, and this is called as what? A differential equation, differential operator, and equation 4 is called as differential equation, and this equation is known as what? A Poisson's equation, or it is also called as a differential equation. And del square is called as a Laplacian, and Laplacian is a nothing but the scalar operator. Now operator del square involves the differentiation with respect to more than one variable. Hence the Poisson's equation is a partial differential equation. Hence Poisson's equation is a partial differential equation. Poisson's equation is a partial differential equation, and which may be solved once we get the dependent variables, say x, y, and z, and appropriate boundary conditions are also there. And from this we have to consider in a rectangular coordinate system, First of all, in a rectangular coordinate system, we have to write del square is equals to del square v is equals to dou square x upon dou y square plus dou square y upon, first of all we have to write that is dou square v upon dou x square plus dou square v upon dou y square plus dou square v upon dou z square. This is a Laplace's equation in a rectangular coordinate system, that is del square v is equals to dou square v upon dou x square plus dou square v upon dou y square plus dou square v upon dou z square. This is the equation we have to consider. First equation, this is equation number say 2, and this is called as a third, that is Laplacian equation in rectangular coordinate system. Similarly, we have to write that is Laplacian equation in spherical coordinate system. In spherical coordinate system also we have to write that del square v is equals to 1 upon r square is equals to 1 upon r square, where what are the coordinate for a spherical coordinate system, that is r, theta and phi are the coordinate for the spherical coordinate system. So we have to write that del square v is equals to 1 upon r dou by dou r into bracket r square dou v by dou r. This is the term for what we have to say that r, 1 upon r square dou by dou r into r square dv by dr, and second term we have to write that is plus 1 upon r square into sine of theta into bracket what we have to say that dou by, this is what we have to say that dou by dou theta, 1 upon r square sine of theta into dou by dou theta sine of theta into dou v by dou theta. This is the term for theta. First one is 1 upon r square dou by dou r square into dv by dr. Second term is 1 upon r square sine of theta dou by dou theta sine of theta into dou v by dou theta. And the last term is 1 upon r square sine square theta plus 1 upon r square sine square theta into last term we have to consider 1 upon r square sine square theta into d square v by dou phi square, d square v by dou phi square. This is the last term we have to consider for a spherical coordinate system. This is the second equation we have to consider in the spherical coordinate system, where r is the distance of radius and theta is considered as a polar coordinate. Theta and phi are considered as what we have to say that polar coordinate. In third we have to say that cylindrical coordinate system. Many times question may be asked on that for derived Poissons equation, for write a short note on Poissons equation, and sometimes you have to write a short note on Poissons equation, also deduce the form of a Laplacian equation in rectangular coordinate system, spherical coordinate system, and also what we have to say that cylindrical coordinate system. In cylindrical coordinate system you have to consider that del square v is equals to 1 upon r dou by dou r into r dou v by dou r. This is the first term, that is 1 upon r dou by dou r into r into dv by dr, and second term 1 upon r square dou square v by dou theta square, 1 upon r square dou square v by dou theta square, plus last term is dou square v by dou z square. And this is a Laplacian equation in the cylindrical coordinate system, where r is the perpendicular distance and theta is considered as azimuthal angle about the axis. This is considered as, say, here r is the radius, magnitude of the radius, theta is the polar coordinate, where r is the perpendicular distance from the axis of the cylinder, and phi is considered, theta is considered as a azimuthal angle. This is about the Poisson's equation in the different forms. Just we have to remember the Poisson's equation. First of all, we have to remember differential form of the Gauss law in electrostatics. What is the differential form of the Gauss law in electrostatics? That is, divergence of E bar is equals to rho upon epsilon 0 is the form. Divergence of E bar is equals to rho upon epsilon 0. This is the differential form of the Gauss law in the electrostatics. But we know that the electric field intensity is nothing but the minus of the gradient of potential, say, V, and so substitute that value, divergence of minus of gradient of V, rho upon epsilon 0, and taken minus sign is outside, that is divergence of gradient of V is equals to rho upon epsilon 0. But we know the property, that is divergence of gradient is nothing but del square V, and that is equals to minus rho upon epsilon 0. Here rho is called, del square is called as what? A Laplacian operator, and this is a differential operator, and then we have to say that del square is equals to minus rho upon epsilon 0 is nothing but the Poisson's equation, standard form of the Poisson's equation. Del square is nothing but the scalar operator, and this can operate the function in different coordinate. What we have to consider, that is say x, y and z in the rectangular system. We have to consider rho of x, y, z, and so the Poisson's equation in the rectangular coordinate system can be written as del square V is equals to dou square V upon dou x square plus dou square V upon dou y square plus dou square V upon dou z square. This is the form of the Laplacian equation in the rectangular coordinate system, that is x in terms of x, y and z. In the spherical coordinate system, we have to consider the coordinates are r, theta and phi. So we have to write that del square is equals to 1 upon r square dou by dou r into bracket r square into dou v by dou r, then plus 1 upon r square sin of theta, dou by dou theta, sin of theta into dou v by dou theta. Then last term is 1 upon r square sin square theta is equals to dou v square by dou phi square, dou v square by dou phi square. And in the cylindrical coordinate system, we have to write that is r, theta and z. We have to r the coordinate for the cylindrical coordinate system, that is del square V is equals to 1 upon r dou by dou r into r dou v by dou r plus 1 upon r square into dou square v by dou theta square and plus this dou square v by dou z square. This is nothing but the Poisson's equation. I hope we have to understand all the different forms of the Poisson's equation in spherical coordinate system, rectangular coordinate system, and also we have a cylindrical coordinate system. Write down all the points are very important. The question may be asked on that. Derive the Laplacian equation, derive the Poisson's equation and reduce the different form in the rectangular coordinate system, spherical coordinate system and cylindrical coordinate system. Write down. Thank you. Also, we have to discuss one more important point. Laplace's equation. We have to discuss the Laplacian equation. We have to deduce the Laplacian equation from the Poisson's equation. First of all, we have to consider in certain classical electrostatic problems involves a conductor, and after that we have to consider all the charges are found on the either surface. All the charges are found on the either surface of the conductor or in the form of fixed point of the charges. So we have to consider a rho is equals to 0. Rho is equals to what? 0. for when the charges of the all the charges are appears on the surface of the conductor, so we have to consider that the surface charge density is zero by by Poisson's equation. So Poisson's equation becomes, what is the Poisson's equation? That is del square into V is equals to, what we have to say, that minus of 0 upon epsilon naught, and then we have to say that del square V is equals to 0. Del square V is equals to what? 0, and this is a Laplacian equation. Laplace's equation. And here we have del square is equals to, what we have to say, that dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Sometimes multiple choice question may be asked on that. Which of the following is the form of Laplace's equation? So we have to write that del square V is equals to 0. This is nothing but the Laplace's equation, and where del square is nothing but the operator in the rectangular coordinate system, dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. And here solution of Laplacian equation reduced to Laplace's equation is reduced to, what we have to say, that is v1 v2 dot 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 vn, v1 v2 dot 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 vn. In terms of this, we have to consider the solution of Laplace's equation. Theorem 1, that is v1 v2 vn, all are the solution of Laplace's equation. v1 comma v2 dot dot vn, all are solution of Laplace's equation. So we have to write that all are the solutions of Laplace's equation. So that V is equals to, we have to write that, therefore V is equals to C1 into V1 plus C2 into V2 plus dot 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 Cn into Vn. This is the we have to consider, that is V, and where C's are arbitrary constant is also the solution. Are also the solution. Therefore del square V is equals to, we have to write that, is del square into C1 V1 plus del square into C2 V2 plus dot 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 del square into Cn Vn. Take the C1 V1 and Cn are the common factors. Therefore we have to write that del square V is equals to, finally we have to write that C1 into del square V1 plus C2 into del square V2 plus dot 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 Cn into del square Vn, and finally we have to write that is equals to del square V is equals to what? 0, because Poisson's equation we have to write that is through the use of theorem 1, we may superimpose two or more solutions of Laplace's equation in such a way that resulting equation satisfy the given set of arbitrary condition. This resulting equation can be satisfied the arbitrary solution of the Laplace's equation, that is del square V is equals to 0. This is, we have to say, that del square V is equals to 0. This equation can be obtained from Laplace's equation. What is the Laplace's equation? Del square V is equals to minus rho upon epsilon 0. And if all the charges are on the surface, at that time we have to say that surface charge density is nothing but the 0. So the Laplace's equation is del square V is equals to 0. And when del square is the d square x upon dy square plus dz square, this is nothing but the Laplace's operator. And solution of this equation is considered as v1, v2, v3 dot 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 vn. Theorem 1 we have to consider that if v1, v2, v3 dot dot vn all are the solution of Laplace's equation, then we have to write that v is equals to c1 v1 plus c2 v2 plus c1 v1 plus c2 v2 plus dot 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 cn vn, where c are the all the c's are the arbitrary constant, means c1 c2 c3 dot dot cn. Therefore the Laplace's equation becomes del square into c1 v1 plus del square into c2 v2 plus dot 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 del square into cn vn, where we have to consider c1 c2 c3 are the constant taken out, and finally c1 into del square v1. Del square v1 is nothing but 0. c2 into del square v2, that is nothing but 0. cn into del square vn is nothing but 0. And something is 0, something into 0, that is called as 0. And finally we have to write that del square v is equals to 0. So all the equations satisfy the arbitrary solution of the theorem 1, and that is called as what? A Laplace's equation. Okay, thank you.